Hi, and welcome back to The Joy of Ray Tracing, a video series in which we make several ray tracers from scratch. On the last episode, we took a look at vectors and how we can do certain mathematical operations on vectors, like addition, subtraction, and scaling. And although we covered what it means to add and subtract and scale vectors, we didn't really talk about what it means to multiply two vectors together. And that'll be the main focus of today's episode. So we're going to take a look at something called the dot product, which is one of the ways in which vector multiplication is accomplished. And as we'll see throughout this series, the dot product is one of the most important vector operations that you can do. The dot product shows up everywhere in computer graphics. So as soon as we add this new dot product function to our vector library, we're going to put it to good use. And one of those uses is defining a plane in 3D and also performing a ray versus plane intersection test. So as soon as we know how to do the dot product, we can use it to define a plane like a ground plane and raycast against that plane in order to visualize it in 3D. So let's take a look at what we're going to do today. Today's to-dos. First, we're going to take a look at the dot product, and that is one of the ways in which you can multiply two vectors together. And then we'll take this new dot product and add it to our JavaScript vector3 library that we created last time. And if you recall from the last episode, we talked a little bit about rays and how rays are mathematically defined. So we had said how all rays have an origin, which is a point in 3D space, and then they have a direction, which can point in any direction, but usually it is confined to a unit circle in 2D or a unit sphere in 3D. But I didn't give you the full picture last time because there's one more element of array that we can add to it, and that's called a t parameter. And the t parameter allows you to slide a point along that array in that direction that it's pointing in. And so we'll take a look at how to do that in a moment. Then we'll use our new dot product function to define a plane in 3D. And once we have that plane defined, we can use a ray to raycast against that plane and find out where it intersects the plane. And that's where that t parameter that I spoke of a moment ago comes into play, because when you perform a ray versus plane intersection test, it'll give you back the t parameter. And that t parameter will tell you how far you need to go along that ray until you hit the surface of the plane. And this is not really related to the dot product, but I just wanted to add this in really quickly to our vector3 library, and that's called the linear interpolation function. And so it has many names in computer graphics. You might see blend or lerp, which is short for linear interpolation. And the name that I like to use is called mix. And so all those terms mean the same thing. So basically you're interpolating between two vectors, and those can be points in space, or they can be directions, or they can be colors even. So it doesn't matter what kind of object they are, but you can use this mix or blend function to do a linear interpolation between the two values. And as you know by now, I really like to do at least a little graphics programming on every episode. And so at the end of today's episode, we are going to raycast a plane. And so we will visualize a ground plane in 3D. And then if the ray hits the plane, we will draw it as a green color or grass color. And if it doesn't hit the plane, if it misses the plane and hits the sky, then we'll color that a bluish color. And by doing that, we'll be able to visualize the plane against the sky and create our first 3D scene today. So I'm really excited to do that. So let's get started. First, let's start with the dot product. And so to help introduce this new topic, I'm going to use my OneNote app here. Okay, so as we've done before, we start out with two vectors, vector u and vector v. Vector u has the components of 2, 3, so its arrow tip ends at 2 in the horizontal axis and 3 in the vertical axis. And vector v is just in the horizontal axis, so it has 4 units in the horizontal and 0 in the vertical. And I made vector v lie flat in the horizontal plane because it'll help make the visualization a little more apparent. So what does it mean to multiply vector u with vector v? Well, many years ago when I was just getting into computer graphics and I thought about this multiplication operation between two vectors, I thought that it was just simply you take the x component of one and multiply it by the x component of the other, and then you take the y component of one and multiply it by the y component of the other, and then you just get a new vector. Well, that is a valid operation, and that's called component-wise multiplication. And we actually will add this later on down the line when we want to multiply two colors with each other. So that'll be useful later when, say, we want to multiply a surface color times a light color. And so you can multiply each component and then you'll get back a resulting color of the light multiplied by the surface color. And so we will actually use that simple component-wise multiplication. But that simple operation doesn't mean much in linear algebra. And recall that we're borrowing all these vector topics from the world of linear algebra. And so linear algebra defines vector multiplication in two main ways. And so one is called the dot product, and the other is called the cross product. And so the dot product is the simpler of the two, and that's the one we're going to take a look at today. We will get to the cross product in a future episode when we add a camera to our scene and we want to be able to point it in a certain direction or rotate the camera. Now, the dot product itself has a couple of different names that you might come across. Typically, the name dot product is the one you'll hear most often, and that's the one we will use in this series. And if you take a look over here in the top left corner, you'll see a dot right here, so it's u.v. And that's where the name dot product comes from. So it's pretty easy to see where they got that name from. Now, two other names for the dot product are the inner product and the scalar product. And so if I had to choose between those two, I would pick the scalar product because that actually reflects what you get out of the multiplication of one vector and another vector. So let's take a look at how the dot product is defined algebraically, and then we'll take a look at how it's defined geometrically or more visually. So to do a dot product between vector u and vector v, you take the x component of vector u and multiply it by the x component of vector v. And then you put a plus sign, so adding, and you multiply the y component of vector u with the y component of vector v. And so you'll add all those together, and then you'll just get a simple number as a result. So let's take a look at that now. So vector u, we take the x component and multiply it by the x component of vector v. And then this is the important step. You have to put a plus sign here because we're going to add everything up. And now you do the same for the y components. So it's the y component of u times the y component of v. And that will equal a simple number. So let's take the values for u and v and fill them into this dot product operation. So the x component of u is 2 times the x component of v, which is 4, plus the y component of u, which is 3, times the y component of v, which is 0. And remember, typically in math, we do the multiplications first, and then we do the addition last. which follows the order of precedence. So 2 times 4 is 8, plus 3 times 0 is 0. And therefore our result is 8. So as you can see, when you multiply two vectors together, you get a number. And that may seem counterintuitive, but remember that we're using concepts from the world of linear algebra. And that's how this first type of vector multiplication, or the dot product, is defined in the world of linear algebra. Now, just looking at these two vectors, vector u, which is 2, 3, and vector v, which is 4, 0, when you do the dot product, you get 8 back. And so that might not seem very important, but let's take a look at what that means geometrically now so we can actually see visually what it's doing. So I'm going to draw a picture of a light source. Let's say we have the sun up here, or a bright light source, and it's high noon, so the sun is directly overhead. So it's casting light downward in this direction. And so what we do is imagine that vector u is casting a shadow on vector v. And so let's draw a dotted line from the tip of u downward onto vector v. And now we're going to draw an imaginary shadow on vector v. So if you imagine vector u is blocking some of the light to vector v, we can draw a shadow in purple here. And so let's note the length of this shadow. We can see that it goes from 0 to 2, so it's 2 units long. So let's write a 2 there. So in geometry, that shadow is called a projection. What we're doing is taking the projection of u onto v. And so whether you think about it as a projection or a shadow, it's the same kind of thing. I prefer to think about it as a shadow. So you have a bright light source above everything, and it's casting a shadow of the first vector onto the second vector. And that's why I made vector v lie flat in the horizontal plane, because it's easier to see this projection as a shadow. But one thing to remember when you're doing a projection like this is that the dotted line has to be at a right angle or perpendicular to the second vector. So the dotted line forms a 90-degree angle with the second vector in the dot product. And then just as we did with the shadow, let's note the length of vector v, where the shadow is falling. So again, I made this horizontal so it's easy to see the length. We don't have to do the Pythagorean theorem on this one. We can just see that it's 4 units of length because there's no vertical direction. So it goes from 0 to 4, and therefore we can write that it's 4 units in length. So I'm going to put that right here. So now we have a purple 2 that represents the shadow of u onto v, and then we have a green 4 which represents the length of the vector v itself. And so geometrically, the dot product is defined as the length of the projection of vector u onto vector v multiplied by the length of vector v. So now let's just plug in those numbers that we have. So the projection we said was in purple here. So the projection, or the length of the shadow when you drop u onto v, is 2. So we write 2 in purple times the length of v. And we had said that that length was 4 in green here. So let's write that in green. And hopefully you can see where this is going. So lo and behold, when you multiply 2 times 4, you get 8, which is the exact same answer we got when we did the dot product between the two vectors. So that may or may not have made it more apparent what the dot product is doing. But just remember, there's multiple ways of defining the dot product in linear algebra. And so The first way we looked at was the pure algebraic way. And so that was the x components times each other plus the y components times each other. And that gives you just a plain number. And then the second way of looking at it was you drop a shadow of u onto v when you do u dot v. And that equals the length of that shadow, or the projection, times the length of the vector that you're projecting onto. So in this case, the length of the projection was 2, and then the vector which it was being projected on is the length of 4, and then when you take 2 times 4, you get 8, which is the same answer. Now there actually is one more way in which we can define the dot product, and that has to do with the cosine of the angle between the two vectors. And so we will look at that more in future episodes when we're doing lighting, but I just want to show you one consequence of doing this dot product when the vectors are perpendicular to each other or at right angles to each other. So let's take a look at that real quick now. Okay, so here's another situation in which we want to find out what the dot product is between these two vectors. And once again, vector v is flat in the horizontal axis only. I think I mixed around the green and the red. I think I had u is red and v is green, so I apologize for that, but typically the right vector is red and the up vector is green, so I may have had it mixed up in the last slide. But anyway, it doesn't matter which you use for the colors. This means the same thing. So now vector u, instead of pointing diagonally up and to the right, is pointing straight up. And so again, we have our bright light source like the sun up here, and it's high noon. And so it's casting the light rays downward, straight down. And so let's take the purple pen and draw a projection or a shadow. So going from the light source, if we head downward along this green vector and project it, we end up with a single point. And remember, points in geometry don't really have any dimensions. So there's no thickness or width to the point. So it's infinitely small. And therefore we can say it's 0 length. So what does that mean to have a shadow of 0 length in your dot product operation? So let's take a look at it from the algebraic point of view. And so remember that we said to do a dot product between two vectors, you take the x components and multiply them together of each vector, and then add that to the y components of each vector multiplied together. So ux times vx plus uy times vy. And so when we plug those numbers in, ux was 0, so we put a 0 there, times the x component of vector v, which was 4, so 0 times 4, plus, and then the y component of vector u, which is 3, so we fill in a 3 there, times the y component of vector v, which is 0. So now we find that when we do this operation, 0 times 4 is 0, plus 3 times 0 is also 0. We get a final answer of 0. And therefore, geometrically, we can say that when there's a 90-degree angle between u and v, so u is perpendicular to v, and you do a dot product between u and v, then the result is going to be exactly 0. So in this case, u dot v equals 0. And that's actually a very useful property because we can do a simple dot product test on two vectors to be able to see if they are truly perpendicular to each other or at right angles to each other. And we will use this perpendicular property when we get to defining a plane, so we can eventually raycast against that plane and visualize it in our ray traced image. And now let's take a look at how that can help us define a plane in 3D. So here I've drawn in a purple color a flat plane that you can think of as like a ground plane or the floor. And it has no thickness, so there's no thickness in the y direction. But this flat plane here extends to the left and right infinitely and extends back into the computer screen and out of the computer screen for infinity as well. But again, it has no thickness in the y direction, so it has no height. So mathematically, there's a couple ways to define a plane, and you might have seen the standard form, which is ax plus by plus cz plus d equals 0. In this standard equation, the x, y, and z represent a point on the plane, and the a, b, and c represent the components of the normal vector to the plane. And then finally, the d can be considered as a distance from the plane to the world origin. But I'm going to show you an alternate way to define a plane that I prefer, and it's much easier on the eyes as well as the brain because it's easier to visualize this. So let's erase this. And instead, let's start by thinking about what components you need to describe a plane in 3D space. So let's say that we're going to give the plane an origin. So in other words, a point in 3D space where we know that for sure that that is on the plane itself. Let's call that the plane origin. And for simplicity's sake, I'm going to make that 0, 0, 0, so x, y, and z of 0. On our graph here, we can just do purple origin of the plane, and that actually coincides with the world origin of 0, 0, 0. And remember, we're talking 3D now, so we've added the z component to all of our points and vectors. So a plane can be defined as a plane origin. And that's a point in space, so I'm going to put a point above that P there. And then arguably the most important part of a plane is where it's pointing. So we describe that with what's called a normal vector. A normal vector is a vector that is perpendicular to the plane. So if you think of a plane as a huge ground plane, then the normal vector points straight up to the sky. And so it's like you took a big pole and you just stuck it right into the ground. And so that is your normal vector, and it points upward towards the sky. So let's draw that in now. I'll use the orange color. And so that's a vector in 3D space, so it has x, y, and z components. And we'll call that one n for normal. So, and this was P origin. And I'll put a dot above the P origin to designate that as a point. And then the normal vector is a vector of how we think of like a little arrow in space. So that can be written with a little arrow over it. So now let's add that to our definition. And the most important thing about the normal vector is that it has to be perpendicular to the plane, or at a 90-degree angle to the plane. So let's draw a little 90-degree angle here. So just with those two bits of information, the plane origin and the plane normal, we can define the entire plane in 3D space. Let's go ahead and give some x, y, and z values to these vectors. So the first vector is the origin of the plane, which is a point in space. So we had said that that was going to be at the world origin, which is 0, 0, 0. It's at the exact center of the world. So, and I'll put a dot over here. So that's a point in space. By the way, even though we think of this as a point in space or a dot, it's technically a vector. It's a 3D vector. So it has x, y, and z components. So how you interpret it, whether you interpret it as a point or as an arrow, is up to you. And so we're just going to interpret the purple numbers here as a point in space, and that's the origin. And then we're going to interpret these three numbers for the n as a little arrow in space. But they're both 3D vectors. So now we can see if we have a flat plane in the x and z plane, then our normal vector will point straight up. So it won't have any x movement, there's no left and right movement, and it won't have any z movement, which is back and forth movement. So it just points straight up, so it only has a y value. Let's fill in those now. So that's going to be 0 and x, and then 1 and y, because it's pointing straight up, and then 0 and z, because it's not pointing into the computer screen or out of the computer screen. And then once more, we'll put a little arrow up here to denote that that's like a little arrow in space. And I'll go ahead and fill these in on the graph here. So now, using these two bits of information, we can create an equation for the plane that is a little simpler than the one we just looked at, which was ax plus by plus cz plus d equals 0. That's a little lengthy. So let's now take a look at the vector form of a plane equation. And so, like the name implies, it uses vectors to define the plane instead of pure numbers. So this is the plane equation in vector form. And it says that a random point on the plane minus the plane origin dotted with the plane normal equals 0. And so you can read this as a random point that you choose on the plane, and that could be any point on the plane. And you subtract the plane origin, then you take that result and dot it with the plane normal, you'll get a result of 0. And remember, the dot product returns a scalar value, which is why it's sometimes called the scalar product. So all it gives you is a simple number at the end of your calculations. Now, the only thing we're missing from our visualization here is the random point on the plane that I put in this light blue color over here. So let's go ahead and pick a random point on the plane and then do the calculation of the plane equation and see if it works. So just to keep the math simple, I'm going to pick a point that's over to the right just a little bit. So let's pick, that is random point, and it's going to be, so that's 3, 0, 0. So we walked over 3 units to the right, and then 0 units up or down, and 0 units back and forth. And now recall from the previous episode when we talked about vector addition and subtraction, when we do this operation right here, this random point minus the plane origin. So when you do this blue colored point minus the purple colored point here, you get another vector that has 3 components. You'll get a vector that points from the purple origin to the random point that you picked. So I picked this easy point here because we can do that in our mind. So you take the x component of this one minus the x component of that one. So 3 minus 0 is 3, and that'll be the new x component of the new vector. And then the y component of 0 minus the y component of 0 is 0 again. And then the z component of 0 minus this z component of 0 is again 0. So the resulting vector will be 3, 0, 0, which happens to be the same numbers as this one here. And so we'll draw this as a vector now, because you can think of it as a vector pointing from the origin to the blue point. So let's draw that in blue. So I'm going to start at the plane origin and then draw a vector to our random point. And now let's simplify this equation. Now that we've done that subtraction, we can just write vector p, and now it's an arrow in space, so it's pointing to the right. Denote that by a little arrow above it. And dot product with the normal vector should equal 0. And real quick, let's do the dot product on these two vectors and see if it equals 0. And you can kind of guess that it will, because this blue vector here is exactly perpendicular to this orange vector here. So they're at 90 degrees to each other. But let's go ahead and do the simple dot product calculation to verify that. So the dot product was, remember, x times x plus y times y. And like in the past episode, when we wanted to go into 3D with these vector operations, then all you do is just tack on the z component to the calculations. So it's really easy. So we're going to do basically x times x plus y times y plus z times z. And then we'll see if that equals 0. So the x component of vector p is 3, and then the x component of vector n is 0. So 3 times 0 plus the y component of vector p is 0 times the y component of vector n is 1. So 0 times 1 plus, and then finally the z component of vector p is 0, and the z component of vector n is also 0. So 0 times 0. And I'll put parentheses around this to make it just a little clearer. So we do the multiplication operations first, and then we add them at the end. So 3 times 0 is 0. 0 times 1 is 0. And 0 times 0 is also 0. So 0 plus 0 plus 0. And as we expected, we get 0 as a result. And therefore, I'm going to get out my green pen here. We get a big green check mark. Yes. So this point is on the plane. Now, one more thing before we move on is that this plane equation here is an implicit plane equation. So notice that it doesn't really tell you where the points are in 3D space. It doesn't give you that information. All it provides is a test or a proof that the point is on the plane. If you pick any point that's on the plane and you do this calculation, then you should get 0 at the end of the plane equation. I'm going to add that this is an implicit equation. And it's an implicit equation in vector form. So remember, the algebraic form was ax plus by plus cz plus d equals 0, which is a little more cumbersome to work with. But this one is more compact and easy on the eyes. So it's just any point that you can think of that's on the plane minus the plane's origin dotted with its normal should equal 0. So if I chose another point, let's say p equals 27, 0, negative 35. When you did the dot product between this point and the normal of the plane, which is straight up and down, you'll still get 0 at the end. And so that point would be defined as being on the plane. But what if a point is not on the plane? How do you know if that's the case? Well, if we pick a random point, let's say like p equals 1, 2, 3. So we have x movement and we have z movement, but now we have y movement as well. So now it's lifted up just a little bit, 2 units in the y direction. And when you do this dot product between this point and this normal, then you will not get 0. And in fact, if we do it in our heads, because it's kind of simple, so it's 1 times 0 is 0, 2 times 1 is 2, plus 3 times 0 is 0. So that would equal 2 at the end. And so you would get an answer of 2, which is not on the plane. The only way that a point could be on the plane in this instance is if its y component is 0. That means it's flat on the ground. And then it can be anywhere you like in x or z. So as long as it has a y component of 0, you can be assured that it's on the plane. So when I said the dot product was really important before at the beginning of this episode, this is an example of why. Because when you want to define a plane in 3D and using the vector form, then the dot product shows up as part of the definition. So now let's take a small detour and take a look at arrays again and how we can add a parameter called t into the array equation. And that will allow us to move a point up and down the array direction. So let's take a look at that now. Okay, so here I've drawn in an example array, and as you recall from last time, array is defined as having an origin and a direction. And both the origin and the direction are considered 3D vectors. For the sake of simplicity, I'm going to go back to 2D for a moment here while we cover the t parameter in our arrays. And then we'll eventually put this back into 3D. But remember, it's not that big of a deal to add a z component to make it 3D. So we're just going to take a look at it now in 2D. The array origin is considered a point or a location in 3D, or in this case 2D space. And so I have an origin of 1, 2. So I walked over 1 in the horizontal direction and 2 up in the vertical direction. And I placed a pink dot right there, denoting the origin. And then array also has to have a direction, and this direction is also a vector, but it's more like what you would think of a vector as. So it's a little arrow pointing in a direction in space, and it has a length. And so usually we normalize these direction vectors for our arrays. So recall last time that we added a normalize function, and that simply scales down the direction so that it's unit length. So I initially picked this diagonal direction going up and to the right, and it could have gone out a long ways here, but when I normalized it, I found that its coordinates were 0.71 and 0.71. So remember from last time, when you normalize a vector and make it unit length, it can only be 1 or below for every component. And if it's 1 in any component, then the other components have to be 0. So the total length has to add up to 1. And so when you do the Pythagorean theorem on this 0.71 and 0.71, it'll come out to 1 exactly. So I pre-computed that before I drew out this picture here. And now we need the ability to move a point up and down the ray's direction. And so let's go ahead and plot a little point where this ray would end up. So I'm going to use a light blue color here, and I'll name this ray point. And I'll draw a little dot over it so that we know that that's the location in 3D space. It's not really a little arrow anymore. We're interpreting it as a dot or a point in space. I use the same origin plus. Now before I write the direction vector, I'm going to insert a t value. So I'm going to write that in green. So put a lowercase t, and then that's multiplied by the direction. And we can put a little dot above the origin. That's a point in space. And this is a little vector that's of unit length 1. And t itself is just a number. So it can be like 5 or 2.7 or 3056 or something. So it's just a simple scalar number. And what that'll do is the t value will scale the direction, and then we can move along the ray in that direction scaled by the t value, and then we'll end up at a different point along the ray. So let's do the simplest case first and just call t 1. That would be the same as writing this. And I'm going to go ahead and plug in the values now. So the origin was located at 1, 2 plus 1 times the direction vector, which was 0.71, 0.71. And this is easy enough so we can do it in our heads. So anything times 1 is just itself, so we really haven't changed it at all. And so here we have a plus sign, so we need to add these vectors together. And remember from last episode, it simply means you just add the x components and then the y components and you're done. So it's really easy to add vectors. So in this case, it's 1 plus 0.71 and then 2 plus 0.71. So the point along our array is now 1.71, comma, 2.71. Simple addition. And if I go to plot that on the graph here, 1.71 is about here in the x direction, and then 2.71 is about right there. And that's right on that unit circle, the purple circle. So that's what we wanted. So I'm just going to put a big dot there. So this is the simplest case, and that's what we were doing last time. We didn't really have a t-value, so it was kind of like having a t-value of 1, because when you multiply it by something, it doesn't change anything. But now let's multiply it by something else to scale it up. So how about a value of 3? So I'm going to write t equals 3 now. And we'll see how this affects the point along the ray. A point along the ray equals the origin plus 3, which is t, times the unit length direction vector, which is 0.71, comma, 0.71. Now beforehand, I went and calculated this little 3 times 0.71. I'm going to go ahead and distribute this 3 across the 0.71 and the 0.71 in the y spot. So our final equation now is point along the ray equals the origin plus the newly scaled direction vector. And I pre-calculated that to be 2.13. And it's the same for the y direction, 2.13. And now when we add those up, we can once more do this in our mind now. So it's 1 plus 2 is 3.13, and then 2 plus 2 is 4.13. So let's write that out for our new value along the ray. So our new point now is 3.13, comma, 4.13. So now let's put that on the graph here. And so if I go to the right, 3.13, that's approximately right here where my mouse cursor is. And then if I go up 4.13, that's approximately right there where my mouse cursor is. So I'm going to draw a new blue dot right there. And you'll notice that it's in this exact direction of the original direction vector for our array. So what we've done is essentially taken this unit length vector that was unit length of 1 and scaled it up by 3. That's like saying we put 3 of those back to back. So if I copy these and just paste them, now you can see that it's just like having 3 copies of the direction vector. So we do 1, 2, 3 times this amount. And then you get this value here, 3.13, 4.13. Now the other nice thing about having a unit length vector to start out with for this direction vector, this yellow one, is that when you multiply it by any t, then you know it's t in length. So if you multiply it by 5, let's say, you know that your result is going to be 5 units long, because it's like multiplying 5 times 1, which is itself 5. If you multiply it by 27, you know that it's going to be 27 units. It's going to be much longer, but you know exactly it's going to be 27 units long because your original direction vector was within that purple circle. And so it was a unit length vector. And that's why we normalize every direction vector to be an exact unit of 1. And that way we can easily scale it up with this new t value. And up here in the top right corner, I have some examples of different t values. And so I made some copies of this array here, and they're a little smaller, but it's supposed to be the same kind of situation. So it's going up and to the right on each instance, but the t value is different for every instance. So the first one is t equals 1, and then you can see the little blue dot. When we slide it along the ray, it goes exactly to where the arrow tip stops. When t is 2, then it's like moving out 2 of these arrows. So it goes out a little farther, and our blue dot slides farther out in space. And then there's nothing saying you can't have fractional values, so I put 0.2 for this one. And as you can see, it didn't even make it to the end of the arrow. So it just scooted out a little bit, like 0.2 units, and then it stopped. And so that's a valid value for t though. So you can have anything you like. And then the last one, I did a bigger number just to show you how it scales. So I put t equals 4 here. And so it's like having 4 of these direction vectors back to back. And then you get all the way out here. And like I said, you can put in anything for t. It can be in the thousands or hundreds of thousands, or it can even be negative. But the thing is with ray tracing, when we shoot a ray out, we're always concerned with what it can see in front of it, or what it's about to hit. Like if you shoot a ray against a plane or a ray against a sphere, you want to see where it hits and how long does it have to be in that t value to hit the sphere or hit the plane. And so you never want to say, oh, what was behind me? We don't really care about what was behind the ray. We're never going to use negative values for t. It'll always be above 0. And the reason why we don't do t equals 0 is because that would mean that the ray didn't go anywhere and it doesn't have a direction anymore, because when you scale the direction by 0, it's 0, 0, and then you just wind up at the origin of the ray. So you haven't gone anywhere, basically. And so that's not really what a ray is. A ray has to have 2 vectors. It has to have origin vector, which is a point in space, and then it has to have a direction vector of at least a little bit above 0. And so it has to point in a certain direction, and you can't have a 0 direction vector. That doesn't make sense. And so we'll always have t equals something above 0, so greater than 0. And I'll write that here. T must be greater than 0 to be a valid value for t. So now, why do we go through all this and talk about adding a scaling value to our direction, which is the t value? Well, when you do an intersection test between a ray and an object, let's say a ray in a plane, as we're about to do, or a ray in a triangle, or a ray in a sphere, or a ray in a cylinder, doesn't matter what it is, you are asking that function to give you the t value back. And so whenever we do a intersection test with a ray and plane, let's say, we want to know how far will it be till that ray hits the plane. And then your function will give you back the answer, which is just a simple number. And you use that as the t value, and you use that resulting t value back in your ray equation, and then you can move the ray along its direction in that t value and move out to where it hit the object. And so we're going to take a look at that now and do an example of a ray hitting a plane. And we'll see where this t value comes into play. Okay, in the interest of time, I went ahead and drew this out so I wouldn't have to draw it in real time as I'm trying to explain it. So we have our plane in purple here, as we did a moment ago in the previous whiteboard. Remember, to define a plane, you need 2 things. You need the plane's origin, or a point that you're absolutely sure is on the plane itself. And you need a normal vector that points perpendicular to the plane. Oh, and I don't know if I mentioned this a moment ago, but the normal of the plane that sticks up, the orange vector here, vector n, that is also usually normalized. And so we make that a unit length of 1 exactly, no matter which way the plane is pointing. So the plane may be facing like this, and then the normal vector would look like that, but we would shrink it down to be a unit length of 1 exactly. or in this case, it's easy because it points straight up, so you know it must be 0, 1, 0. And so that makes a normal vector that points up, but it's also a unit length of exactly 1. So now with that information, we can test for whether a ray will intersect with a plane, and if it does, we can see where in 3D space it'll intersect that plane. And so remember that our ray is defined as having an origin and a direction. And so the ray has an origin, and that's in pink here. And then it has a direction vector, which is normalized to be a unit length. And so that is denoted by the letter D here, so the direction of the ray. Now to find a point along the ray, you add the little t parameter to it. And so this little t in the green color here will scale up this direction, and that way you can move along this ray in its direction. Now since this t is a singular number or a parameter, we call this a parametric equation. And therefore it's an explicit equation. So whether you say explicit or parametric, they both mean the same thing. Remember back when we talked about the plane equation, we said that the plane equation was implicit. And so here's the plane equation. It says a point on the plane minus the plane origin dotted with its normal equals 0. And so that doesn't really give you a point along the plane at all. It just offers a nice little test to see if a point is on the plane. And if it satisfies this equation and it's equal to 0 at the end, then you know that the point is on the plane. And that'll work for any point along that huge ground plane that we're about to draw. And so going back to the ray equation, we have an exact parameter now, so a scaling factor, which is this t, and it's going to scale the direction, and therefore we can find an exact point along that ray just by scaling the direction. And so it does give you an exact point in 3D space. So that's why we call it an explicit equation, because it's actually giving you a real vector location in space. So now if you look at my diagram here, I have a ray with its origin pointing down. And it's kind of like we're looking down at our feet. Our head is up here and we're standing on this ground plane. We want to know, where is it going to hit this? And so here's the things that we do know. We know the origin because we ourselves are the origin. Our eyes are the origin. So we can just put ourselves wherever we like. And then we can have ourselves look in any direction. And so we can define that as well. But what we can't say for certain is what t is. What is the value of this t variable here that will make this stretch out until it hits the plane? That's the big question. Because if we knew what the t value was, we can just go back and plug it into this equation, our explicit equation, and then it'll give us an exact point in space of how much to move along that ray where it intersected the plane. So the only variable we don't know in this whole process is t. So in order to answer this question, long ago, someone very smart figured out that you could combine both the ray equation and the plane equation into one equation. And so even though the ray is an explicit equation with a parameter, and even though the plane is not explicit, it's implicit, we can still combine those and then extract the t value or solve for t. And so if we put everything on one side of the equation and then leave t on the left side of the equation, then we'll have our answer at the end of the calculation. On the whiteboard coming up, I'm going to show you how we do that, how we combine both equations and then solve for t. And it's actually not too hard. It does require a little bit of algebra, and you might have to brush up on your distributive properties and things like that, but it's no harder than something you would get as a student in an Algebra 1 class. When we combine these two equations, the explicit ray equation and the implicit plane equation, we just go ahead and assume that there is a point of intersection in the ray's future. So that's what we call point of intersection right here, this PI, point of intersection. So I put an example point of intersection here. So I set it to 3, 0, 0. So we walked over right 3 units, and then no units up and no units into the screen or out of the screen. So it's directly to the right, and therefore we have a right angle between this vector and the normal vector of the plane. And so if we could find a point along the ray where it satisfies this vector being at 90 degrees to this normal vector of the plane, then we've found our intersection point. And so when you put it back into the plane implicit equation, which is kind of like a test for whether something's on a plane or not, you can say, well, my point of intersection, which was 3, 0, 0, this little blue dot right here, minus the plane origin. So when you do that, you get a vector, and that's this P right here, this P vector. And so this is this light blue vector right here. When you dot that with the N, the normal vector of the plane, then you should get 0. And so on the next whiteboard, when I actually do the algebra for this, we kind of assume that there is a point on the plane which satisfies all these equations. And so we're kind of optimistic in that sense. So we just assume, yes, there will be a time where the ray will hit. And so we just plug in the ray equation into the plane equation. And by definition, our point will have to satisfy this dot product equaling 0. And so all we have to do is just solve for t then. And then whatever t we find will make this true. So point of intersection minus plane origin dotted with its normal equals 0. Okay, so now we get to the heart of the intersection test between a ray and a plane. So we want to know whether the ray will hit the plane, and if so, how far, or what's the t value, how far do we need to go along its direction in order to get to the intersection point. So now let's just recall the equations for the plane and the equation for the ray. The plane equation is a point on the plane, so we're going to call this the intersection point, minus the plane's origin, and let's put that in parentheses, dotted with the normal vector of the plane, must equal 0. And again, that's an implicit equation. It's not giving you any exact points, but it's offering an exact test to test whether a point that you pick will be on the plane or not. Now the ray equation is explicit or parametric. An array, recall, is its origin plus a scalar value that we call t times the direction of the ray. And that equals a point along the ray. So the t value scales the direction, and then we know how far along the ray's direction we need to go to obtain that point. And so notice I used the same light blue color for the point along the ray and the intersection point back in the plane equation, or just this can be any point in space, so long as it equals 0 when you do this calculation. So what I was saying on the last whiteboard is there is someone, I don't know who is credited for first coming up with this, but they figured out if you replace this pi with this equation, then you can solve for t. So what we're going to do is take the ray equation, which is explicit, and plug it into the implicit plane equation, and then replace this pi with all this OR plus TDR. So in other words, I'm going to replace that with this. And so let's rewrite the equation now. So there's our formula for the ray. So the origin plus the scaled direction. That'll give us a point along the ray. And then we just continue with our plane equation as it was. So minus the plane origin. And now we can put all that in parentheses. And then you take the result and dot product with the normal vector of the plane. And I'll put P here for plane. Normal vector of the plane equals 0. So see what I did there? I took this point of intersection here that satisfies the plane equation and I replaced it with a point along the ray. And so I put all these variables, so the origin plus the scaled direction right here. And then I just continue on with the plane equation. So that says minus plane origin and then dotted with the normal of the plane equals 0. The solution now is if we can find a t value of something that's greater than 0, because remember we're only interested in what the ray sees in front of it. We don't want to know any negative values or anything. So we only want to concern ourselves with values above 0. If we can find a t value like that that satisfies this entire equation and it equals 0 at the end, then we'll have found our point of intersection. So now our job as algebraists is to get t by itself on one side of the equation and then solve for t. Now, one thing I should mention before we move on for solving for t is that the dot product is distributive. So for instance, if you have a dot b plus c, and these are all vectors, you can kind of look at this dot as a multiplication in regular algebraic expressions. So we can distribute this a to across the b and then across to the c. So we can rewrite that as a dot b plus a dot c. And remember, all these are vectors. So vector A has x, y, and z components, and then B has x, y, and z components, and C has x, y, and z components, but I just represented them here as capital letters. So A dot B plus C is the same thing as A dot B plus A dot C. So it has the distributive property. Also, one thing that I forgot to mention is that A dot B equals B dot A. It doesn't matter in which order you do the dot product. You'll get the same result. So it does have the commutative property, just like regular multiplication. So you can do 3 times 5 equals 15, or you can do 5 times 3 is also 15. And so A dot B is the same thing as saying B dot A. And then A dot B plus C is the same thing as A dot B plus A dot C. Because we're about to use this distributive property on the next step in our simplification of this equation. Now remember, our ultimate goal is to get t by itself, this little green t right here. So what I'm going to do is pull this part out of these parentheses and then dot that with n. So we're going to use this distributive property now. And you'll see why in a minute why I'm doing this. So when we take that out, we're left with O. And I'm not going to write the subscripts anymore just to keep it less busy. So now let's take this origin minus the plane origin and put those two together. Now that's still dotted with n, the normal. Now we use the distributive property and take out this TDR here and keep the sign so it's a plus sign there. Plus And again, I'm not going to write the subscripts just to keep everything neat. So TD, and then that is dotted with N as well, using the distributive property. And all that is equal to 0. So remember, we want to get this T on the left side of the equation all by itself eventually. So let's take this whole section here and subtract it from this side of the equation, and then move it over to this side, the right side of the equation. So I'm going to underline this. So I'm going to take all that and minus all that from this side. Actually, I'm going to remove that line because it looks like a division. Now, by doing that, it effectively takes it off this side of the equation, so we can cross this out now. And what you do to one side of the equation, you have to do to the other side of the equation, as we learned in algebra. That leaves us with TD dotted with the plane normal equals, and let's not forget this sign right here, so negative ray origin minus plane origin dotted with the normal of the plane. All right, so we're getting closer to our goal of isolating the green t value all by itself on the left side of the equation. Now, we can make this side look a little better by just swapping these two vectors, because when you distribute this negative sign, it becomes minus O and plus P. So how about we change it to plus P minus O, or just P minus O. And so we can rewrite this a little neater. And still dotted with the normal vector. And I'll draw like a little arrow here, showing that I just swapped these and applied the negative sign to both. So the O became negative and we put it over here, and then the negative times negative is a positive P, and so we put the positive P over there. That looks much neater now. So there's only one last step, and that's to get T by itself. Since this T is multiplying by the D dot N, let's just divide this whole thing by D dot N, and that'll cancel out the D dot N, and we'll be left with T. So let's try that. And now we can cross out this part as well, because anything divided by itself is 1. And now we finally get the T by itself, which was our goal. I'm going to write everything out neatly now. Since we divided by D dot N over here, we're going to divide by D dot N on the other side of the equation. And there we have it. So we have successfully got T on the left side of the equation, and we now have solved for T. And that equals, you can read this as the following: the plane origin minus the ray origin dotted with the plane normal divided by the ray direction dotted with the plane normal. And we can go ahead and, let me put the subscripts back in there, and we'll use this equation to write that in code in our JavaScript library that handles ray plane intersection tests. So that's the plane origin. This is the origin of the ray and the normal of the plane, and then the direction of the ray and the normal of the plane. And notice that nowhere in here appears the actual intersection point. That's because we've done this substitution where we substituted the explicit ray equation with its t value into where we had the point of intersection before. So using that little trick that someone came up with all those years ago of how to do a line and a plane intersection test, we are able to isolate t and then analytically solve for the value of t by doing a simple vector subtraction and a dot product over another dot product. And the dot product itself, as you saw before, is just a couple of multiplications and a couple of additions. So it's really not that much calculations in the end. And so although I've spent time deriving this equation and it's taken a while, when we actually implement this in code, it's only going to be about 5 or 6 lines of code. So to wrap this up, all you need to figure out where a ray will intersect a plane is the ray origin, the ray direction, and you need the plane origin and the plane normal. If you have those 4 items of information, then you can solve analytically for t just by manipulating algebraically the terms and getting t on one side and solving for t. And so once we get this t value back, we can simply plug it back into the ray parametric equation, the one that says O plus TD equals the point along the ray. And then when we plug it back into that, it'll give us the exact point out in space where the ray intersected the plane. Now, this is assuming that there is an intersection. So what happens when there's no intersection? Well, the t value will come back as either 0, and that'll mean that the ray is going along the plane, and so it'll never intersect. Or like if we were looking up at the sky and the ray goes up into space and never hits the ground plane. And so in that case, the t value will end up being negative. And so we can easily test for that. So if t is negative, we know we're looking the wrong way and we'll never intersect the plane. So as long as t is a positive value above 0, then we know that there is an intersection point along the ray in which it's going. And so we can just go ahead and plug that back into the simple ray equation and get that point out in space. And then we can draw that to our screens and visualize these shapes like planes and spheres and cylinders and so forth with these simple equations. So I think that's really cool. The fact that we can just manipulate these symbols around and get it to where we're solving for t and then end up finding out where we intersect the rays with all our objects in the scene. So now that we've done all this, let's go into Visual Studio Code and code all this up and add our new dot product function to our vector3 library in JavaScript, and also this new equation for testing where a ray intersects with a plane. Okay, I just wanted to show you this real quick. This is how a linear interpolation works. And it goes by different names, so you might see blend or lerp. I'll add that to the list here, which is short for linear interpolation. And I prefer the word mix because you're mixing between 2 values. So linear interpolation sounds really fancy and stuff, but all it really means is you're just blending between 2 different states or 2 different numbers. So let me draw this out. So let's say I have value A, and over here I have value B. Now A and B can be anything. So in this case, I'm going to make them a color. So A stands for the color red, and then B is the color yellow, as we can see here. So now we'll make a line between them. And here's where the word linear comes into play, because you're sliding along a line. It's kind of like a slider between 2 values. And how you slide between those 2 values is a parameter. And so much like we did with the ray, like sliding along the ray direction, we can use a value that we can again name t. And so t will tell you how much to slide along this line here between these 2 different values. And so if t is 0, then you end up at full value of A with none of B blended in. And if you do t equals 1, then you slide all the way over to B and you have none of A. And so the range of t is, I'm going to move this over, so the range of t is greater than or equal to 0 and less than or equal to 1. And so it's in the range of 0 to 1 inclusive. So it can be exactly 0 and exactly 1 or any value in between. So for example, if you did t equals 0.5, that would move the blending value right in the middle between A and B. And so you would get half of A mixed with half of B. And so in this case, if you mixed red with a little yellow, you would get like an orangish color. So that would be something like this. The blended color would be like that. And these A and B values can be anything you like. They can be a color like it is here, or they can be a normal vector, or they can be a ray direction, or they can be just some pure values that you can just mix between. And so the nice thing about having this t value here is that since it's between 0 and 1 inclusive, then you can just easily dial up and down the blending weight between the two values. So when we add this mix function here to our code in the JavaScript vector3 library that we created last time, it's going to take in two vectors and a t value. And so it'll look something like this. So the new blended color vector equals, we'll create a function called mix that'll take in a vector A, a vector B, and a number that will mix between the two. So we'll call that t. And these are vectors. And again, A and B can be anything you like. They can be like a direction vector or a location or a color vector of RGB. So it doesn't matter what you want to blend between. You can do anything with this function. You can mix between any two values as long as they're the same type of values. And mathematically, how this is achieved is, so the new value, I'll call this C, equals A plus, and then we subtract A from B. So that looks like this, B minus A. That gives us this line segment right here between the two values. So B minus A gives you a vector that points this way. And then we multiply that by whatever t value we passed in. Let's just do a couple of examples to see how this would work if t was 0. Now when you multiply this b minus a times 0, that makes this effectively 0, so it's a plus 0. And so you're left with a. And that's what we wanted, because when we have a t of 0, we should be sliding all the way over here to the left side. So we should be just remaining at the a value. So that equals a. And then let's put in a 1 for t. So now b minus a is the total range, the length of this line, and that's multiplied by 1. So that's the entire length. And now when we add that back to the origin, which is a, we get the slider all the way over to b. And so we've successfully blended all the way to the max, which is b. And now let's do this one more time. Let's say we had a t value of 0.5. So now this range from B to A, which is this line right here, is multiplied by half. And so that's about this far. And then when we add that back to A, which was the origin, we get right in the middle of A and B. And you've successfully blended exactly half of A with half of B. So I'll put that as C, which is a new color, which is kind of a orange color in this case, because when you blend red with yellow, you'll get like a bright orangish color. And so just by changing this little green t value here, we can slide this little blue slider left and right, and then we can get more of A, more of B, or right in the middle, or all of A and none of B, or all of B and none of A. So you have a lot of power over this blending function with just that little T parameter. So I just wanted to show you how this works theoretically, and then we're going to add it into the code. But it's super simple. All it is this line right here, basically. And you just do that for the X component of the vector, then you do it for the Y component of the vector, and then you do it for the Z component of the vector. And again, you might see this referred to as blend or lerp or mix. And I use the word mix because that's a good description of what we're doing. So we're mixing between two values. We're adding a little of this and adding a little of that and mixing it together. And in fact, when we get to the GPU ray tracing later on in the series, there's a function that does linear interpolation that's built into the shader language of GLSL, and it's called mix. So it uses this exact function name for what we're doing here. And so by the time we get there, that mix function will look very familiar, hopefully. All right, so let's open up Visual Studio Code. And we can see what we were working on last time. We just added our ray direction visualizer demo to our repositories on GitHub. So what we'll need to do today is add our new dot product functions and our blending functions, the mix function, and the plane intersection routine that we had just discussed a moment ago. And we're going to put all that into mathutils.js, this file here. But before we do that, I'd like to make a new demo file so that we can raycast against a plane in 3D and visualize that all in a new demo. So let's go to raydirections.html. That was the one we did last time. And we're just going to copy this and create a new HTML file with a different title. Go over to the left here and click on raydirections.html just to make sure that you're in the right directory. And click on New File. And let's call our new demo intersectPlane. So intersectPlane.html. And hit enter. And now you should have a blank file called intersectPlane.html, and go back into raydirections.html and just select all this code and Control C and Control V into intersectPlane.html. And then right away, I always like to change the title so I don't get confused. So erase raydirections and make it intersectPlane. And we'll change this JS file in just a moment. So let's go and create a new JS file to match this HTML file. And so go into the JS folder and click on Ray Directions just to make sure that you're in the correct directory here. So you should be inside the JS folder. And now click on New File and call this the same name but with the JS extension. So intersectPlane.js and hit enter. And now if you click on raydirections.js, our old file that we did last time, likewise we're going to select all of this and just copy it into our new file. So a shortcut to doing that, you just go up to selection and then select all. And then Control C, go inside intersectPlane.js and Control V. Now before we go any further, I always like to X out of the old files just to make sure that we don't get confused on what we're working on. So click out of Ray Directions, and you can leave raytracingstyles.css up. That's fine. We might work on that in the future, but we're not going to do anything to that today. But it can just remain here in our open tabs. And then click out of Ray Directions. So that's gone. And then we still need math utilities up. We're about to change that in a moment. And one last thing we need to do inside of intersectPlane.html, so go there, is to change the file path of this JS file down here. So currently it's pointing to ray directions, and we need it to point to intersectPlane.js. So just go in here and erase this text up to JS. And then we get to see one of my favorite features of VSCode. So type the / key. I just love it. And so you can select intersectPlane.js. And before we go and change anything to math utils and add our new functions today, let's just make sure everything's working currently. And so let's go down to the right bottom corner here where it says go live. It's very small, a tiny little button down here on the right bottom corner. So click on go live, and that should open up your default browser. Okay, great. So everything's working. It says intersectPlane.html. That's the name of our new demo. And it's visualizing all the ray directions that we were doing last time. So it's the exact same demo as last time. So we will change this in a moment to intersect a plane and visualize a ground plane and a sky in 3D in just a little while. So I just wanted to make sure everything was working first before we go and edit those files. So now let's go back into VS Code and click on mathutils.js. So this is our vector3 library in JavaScript that we had created last time. And so if you recall, we had a notion of a vector3 object and then different functions or methods that you can call on this object, such as set, copy, add. So if you scroll down all the way, we stopped with normalize, which makes a vector a unit length vector of exactly 1. So now we're just going to add on to this file and then give our vector3 library even more functionality. So how about the first function that we add is the dot product function. And so real quick, let's go back to our slides because it's been a while. We've discussed a lot of topics today, and so I want to refresh our memories of what the dot product is algebraically so we can put it into code. So let's go to the old slides here and recall that the dot product means you take the x component of the first vector times the x component of the second vector plus the y component of the first vector times the y component of the second vector. And then in 3D, as we'll see, we just tack on the z components to this equation. So you do another plus, and then the z component of the first vector multiplied by the z component of the second vector, and then you return that, and it should return a number from this dot product function. So let's go and put that into code now. So click here and then hit enter a couple of times, and we're going to add on to the prototype of our vector3 object. So vector3, and you can hit enter when it comes up, dot prototype. You can click there, dot, and we're going to call this function dot. So dot, and then space equals space. And recall that in JavaScript, to add on to a prototype of an object, you use the function expression method of defining a function. We're typing equals here, and we're setting the function equal to this dot method here. So it's called a function expression. We type the keyword function, and it is going to take an argument or a parameter. So it's going to take another vector to dot against. So we're going to call this dot product on the current vector3, which will be like vector u in our whiteboard example. And then vector v will go inside the parentheses. So that'll be the other vector. And so let's just name this parameter other vector. Open parentheses and it'll close it for you, and then type other vector. And it comes up because we've used that name before. And now you can go on to the next line and opening curly brace, and it'll close it for you, and then hit enter. And now we're going to define this function. Oh, and before I forget, I always forget this, put the semicolon after the closing curly brace. Because technically, this equals sign right here makes this a function expression, and it's kind of like an action. You're setting something equal to something. And so you're assigning a function to a method on this object. And so since you're doing an action in JavaScript, that usually requires a semicolon at the end of a statement like that. And so this whole thing you can view as a statement, and we need that semicolon after. Now, technically, you don't absolutely need this semicolon after every expression in JavaScript. So like I said last time, you could actually leave all these off and your program would still run fine. But I just like to be consistent with my semicolons and put them at the end of every statement and expression in JavaScript. So now go back into the body of the function here. And with all that discussion about the dot product and all that time we spent on it, this is going to be a one-liner. So it's kind of ironic that the dot product is so crucial to all vector libraries that you'll see out there, and we will use it on every single ray tracer that we write. And the dot product itself is indispensable when you talk about linear algebra. There's so many topics in linear algebra that use the dot product. And so with all of its importance, it's funny that it's only a couple of calculations that can be fit into one line. So we're going to return, and this is going to return just a number. Remember, it's just a scalar number. That's why it's called the scalar product sometimes. So return, and then we're going to use the keyword this, which refers to this vector 3 that we're calling the dot product with. So this dot x times the other vector dot x. Plus, and then we do the same for the y components and the z components. So it's really simple. So this dot y times other vector dot y plus, and then we just tack on the z components to bring it into 3D. This dot z times other vector dot z, and then semicolon, because that's a statement in JavaScript. Now the dot product needs these multiplications to be done first and then the additions to be done last. And most programming languages have an order of precedence like this, but I always like to add some parentheses in a statement like this just to make sure that the calculations that I want to get done are getting done first and there's no surprises. And so let's enclose the x component multiplication. So you just select this text here up until other vector x and then shift opening parenthesis, and it'll close it for you. It'll place parentheses around this whole thing that you selected. And then just do the same for the y components multiplication. So opening parenthesis. And then lastly, do it for the z components. So select all that and opening parenthesis. So that just makes sure that JavaScript or whatever programming language you're using is doing these multiplications first, and then the additions come last. Now I would like to add the mix function. So let's go down a couple of lines here, hit enter a couple of times, and let's just real quick go back to the whiteboard and see what the mix function was mathematically. So we can put that in code. And here we have the mix function. So this one is pretty easy as well. so there's not a lot going on. So we just do this calculation right here for all the components. So we do it for the x component and the y component and the z component. And so we'll call this function mix, as we discussed earlier, and it'll take a vector a, and then it'll take another vector b, and then it'll take a t-value, or the amount to slide between a and b. And even though these are vectors here, we should do them per component. So we're going to do this little calculation here, this a plus b minus a times t. We're going to do that for the x component separately, and then do that for the y component on the next line, and then do it for the z component on the next line after that. And so we'll have 3 lines of this little simple equation. So let's go and implement that now back in our code. All right, and once again we type vector3 dot prototype dot, and then let's call this mix. So mix equals function keyword, and now opening parenthesis, and we're going to put the arguments or the parameters now that it takes. Let's just call these vector A and vector B as we did before. So comma, and then the next one is vector B, and then a t value. And now hit enter and go on to the next line, and opening curly brace, enter. So in other words, when we call the mix function, it's going to set the vector 3 that we call the mix function on to a blend between vector A and vector B, whatever we supply as those vectors. It could be anything like 2 directions or 2 colors or whatever we want to blend between. We're going to change the value of this dot x, this dot y, and this dot z. So let's do the x components first. So this dot x is now equal to, so this dot x will now be the new blended value. And so recall that we do vector A first and use its x component only. So we're only operating on one component at a time. So dot x plus, and now opening parentheses, and we're going to define the range now. So vector B dot x minus vector A dot x, and the parentheses here ensures that the subtraction gets done first before we multiply it by the t value. And so now we multiply by the t value that was supplied, and then finally you just put a semicolon because this is a statement in JavaScript. And so now we've completed the first component of this blend function, or this mix function. And so now let's just take this whole line and copy it and then paste it twice. So paste it again. And now we just change the components to y and z. So y and z. And go on to the next line, and finally we return this, which is the newly blended vector that you want to contain the new blended value. So return the newly blended vector. Return this. Oh, and I forgot one thing here in this mix function. We need to ensure that the t value that was passed into this function is between 0 and 1 inclusive. If it's outside the range for some reason, like someone accidentally uses a negative value for t, or they increase t until it's past 1, so if they provide like a t of 27 or something, you're going to get unexpected results because you're essentially multiplying that range by that larger value. Or if you supply a negative value, then it'll flip things around. So you'll get unexpected results from the mix function if you happen to call it with something other than 0 to 1 range for t. So let's go on the first line here and just ensure that t is between 0 and 1 inclusive. So go on to the first line here and enter. And then let's set t to a minimum of t itself and 1. And that will clamp it to 1 or below. And so we can use the math library in JavaScript. So math.min. You can see it's a method here. So if you click on there and then opening parentheses, because it is a function in JavaScript, it needs parentheses. And now inside the parentheses, it needs 2 values to compare, and then it'll select the minimum of those 2 values. So we want t itself and then 1. And now that was a statement in JavaScript, so semicolon. So let's say the user passes in like 100 or something. So it'll get here and say t equals math min 100. It'll put the 100 where the t is, comma 1. And it'll select the minimum of those 2 and then set that back to t. So 100 is much greater than 1, so it's going to pick the 1 here, which is the minimum of those 2, and then put that back into t. So it clamps it back down to 1. So the user can't accidentally go outside of our range of 0 to 1. And now likewise, let's do the same for 0 to make sure that t is always positive and not a negative value. So let's go on to the next line and do t equals, call the math object again. And now we use the maximum function, or max for short. So max, and again we're going to use t itself, comma, and now we need it to be higher or equal to 0. So let's put 0. And then once again, semicolon at the end of the line. And now let's say if the user accidentally passes a negative value for t. So let's say they put -2. And so when it gets to this line, it'll go t equals math maximum of t. So it'll put a -2 in here, comma 0. And it selects the maximum of those 2. So -2 is definitely not higher than 0, so it'll select 0. And then it'll put that result back into t, and now you have a completely clamped value for t between 0 and 1. And so it just ensures that someone doesn't accidentally pass a value outside of that where you would get unexpected results. Oh, and I always forget, here at the end of this function expression, we should put a semicolon. And now the last thing we can add to our math utilities file is the routine to test if an array intersects a plane. Let's go down a couple of lines here. So let's go back to the whiteboard where we discussed the intersectPlane function, just to recall what we're going to need to put into this code here. Okay, so here we see the equation for determining the t-value of a ray that will intersect a plane. And although we have like a lot of math here and we derived the equation ourselves, all we really need is this part right here. So the t equals the plane origin minus the ray origin dotted with the plane normal divided by the direction of the ray dotted with the plane normal. That's all we really need to get the t-value that we're interested in. And in order for this function to work, it's going to need to take 4 parameters. Remember that we talked about, so it needs a ray origin and a ray direction. And so here they are right here, ray origin and ray direction. And then it needs the plane origin, where it is situated in the world. So here's the plane origin, and the plane normal. So which way is the plane facing? Is it facing up or tilted or down or wherever you like? So here's the plane normal right here in orange color. So if we have those 4 bits of information, then we'll be able to do this little calculation here and get the t value. So let's go back into the code and set some variables up so we can perform this ray plane intersection test. Now this function is not going to operate directly on the vector3 object that we've been working with and setting the prototype of in the past. And so that's why I named this file math utilities. So it's going to just handle all the math related stuff like vectors and intersection tests and things like that. So even though this is a vector3 library so far, we can just add this ray intersectPlane function down here at the bottom. That way everything is contained within one math file. And since we're not using the function expression method to set the prototype anymore, we can just use the function declaration method, which I prefer. But the only reason we had to use the function expression method here with these semicolons at the end and all that is because when you set the prototype, that's what you have to use in JavaScript. But now we're going to just do a normal function declaration. So you can type the function keyword first, and then the name of the function. So let's call this intersectPlane. I think that's fairly descriptive of what this function does. So intersectPlane, and it's going to take 4 parameters as we discussed. So it's going to need a plane origin, where the plane is situated, the plane normal, which way the plane is facing, and then it'll need a ray origin, where is the ray located in 3D space, and a ray direction, which is where the ray is pointing. And so let's type those out now. So plane origin, comma, the next parameter is plane normal, and then it'll need a ray origin and a ray direction. So with those 4 bits of information, those 4 vectors, these are all 3D vectors, so they all have X, Y, and Z components. So with those 4 bits of information, then this function will be able to do its work and provide you with a t value for your ray that you can just plug in to your ray equation. So now go on to the next line and opening curly brace, enter. Now if we look back real quick at the whiteboard, we need to have the plane origin subtract the ray origin. And in our current code, when we subtract something, it changes the one you called it on. So if we called plane origin subtract ray origin, it's going to change plane origin. And we don't want to change the plane origin each time we call this function. That'll mess everything up. So let's make a vector outside of this function that will just copy the plane origin, and that way we can safely operate on that and just use it and reuse it every time we call the function. So let's go back into the mathutils.js file and go up here above the function intersectPlane and hit enter a couple of times. And now let's create a variable that will hold that plane origin minus the ray origin vector. And that'll be a vector3 itself. So remember, we used the let keyword in JavaScript, so let. And this is going to be a kind of a long name, but I prefer descriptive names over short cryptic names. And so let's make this pretty descriptive of what it is. So plane origin, and we don't have to type out the full word plane origin. So let's just stop at O. So plane O, and then type underscore. Now we need the ray origin, and we can just put ray capital O again, and then one more underscore just to separate all the words out. And let's type out vec for vector. So by looking at this, you can see that it's a vector from the plane origin to the ray origin. And so hopefully someone reading your code, or if you're reading your code after a while of not looking at it, you remember what this is. One of the most difficult things about writing code is what to name things. And now we're going to set it equal to a new vector 3. So new vector 3, and you can click here. And it's technically a function in JavaScript, so we type the opening parenthesis and it'll close it for you. And then it doesn't really need any parameters right now, so we can just click over here at the end and put a semicolon. And going back to the whiteboard again, if you notice on the denominator here of this fraction, it's the ray direction dotted with the plane normal. And that's just a number. And so I want to save that in its own variable, because we have to check whether this is 0, because that means the ray itself is parallel to the plane and it'll never intersect the plane. And we don't want to try dividing by 0 because you might get unexpected results. So let's create another variable that will hold the dot product between the ray direction and the plane normal. Again, let's use the keyword let, ray direction, and I'll just type a capital D meaning direction. We don't have to fully spell it out. And then underscore, and then type the word dot, and then another underscore, and now the plane normal. And we can just put capital N for normal. We don't have to spell it out again. And this will be a number, so we can go ahead and just initialize it to 0. So that will hold whatever direction dot plane normal it turns out to be. And I'm going to scroll up here so we can see a little better. And we need one final variable outside this function, and that's going to be the result of the function. So whatever t turns out to be. And so let's hit enter one more time and type let, and then we'll name this simply result. So result. And again, that's going to be just a number. So whatever t turns out to be. And we can just initialize that to 0 as well. The reason I didn't use t is because we're going to be using t all over the place later in our ray tracers when we're intersecting multiple objects. And so you're going to have a lot of t values flying around. So I rather name it something different just for this function. And so result is a good fit for that variable name, because then it won't conflict with the t value possibly. Now maybe just hit enter one more time to put a space between the variables and the function here. And now we can define the function itself, the intersectPlane function. So before we do this exact calculation here and provide the t value back to the caller of this function, I just want to do a little pre-calculation. So let's use our ray_d.planeN variable and go ahead and do the dot product of the ray direction and the plane normal and save it into this variable. ray_d, and you can click on it when it pops up here, equals. Now we get to use our dot product that we just implemented a minute ago. So it says that we need the ray direction dotted with the plane normal. So type ray direction, and that highlights this right here because that's the parameter that was passed into this function. That's correct. That's what we want. Ray direction, and then dot. Now the word dot, so dot, and then this is a function, so it needs parentheses. So open parenthesis, and then it should be dotted with the plane normal. So let's go ahead and type that. Plane normal, and that highlights this parameter right here, so that's correct, that's what we want. And now at the end of all that, put a semicolon. So in other words, we take the ray direction and perform the dot product with the plane normal. And then we save that as ray direction dot plane normal. And again, that's just simply a number. It's just a scalar number. Now it turns out there is an early out to this function. Let's say if you have a plane that's facing up, like our ground plane that we'll implement in a sec. So let's say if we have a ground plane and its normal is pointing straight up towards the sky. But imagine yourself looking up at the sky, so your head would be above the plane and you'd be looking in the same direction as the normal, right? So if those two vectors are pointing in the same direction or nearly the same direction, then the dot product will be a positive number. And so I didn't really talk about that when we discussed the dot product before, because I'm saving that for a future episode when we talk about lighting and comparing the directions of two vectors. But in a nutshell, when you have two vectors that are pointing the same way, the dot product will be positive. When they're perpendicular to each other, as we did discuss, the dot product will be exactly 0. And we use that to our advantage to define a plane. Now, the last case that you can have is, let's say if your plane is pointing up, like it always is, but your ray is pointing down, and so you're looking physically down at your feet, or you're looking down at the ground. Well, that's good. That's what we want, because then you would see the plane. And so that dot product of a vector pointing up versus a vector pointing down, the dot product of those will turn out negative. And so we can simply test right here if this ray direction dot plane normal is not negative, like if you're not looking down, then we don't even want to continue, because that means you're looking either parallel to the plane surface and the ray will never cross the surface, or you're looking up at the sky, in which case you won't see the plane. So on the next line, let's do a simple check. So if, and then open parenthesis, now we're going to check this value, so type ray direction dot plane normal is greater than or equal to 0. So remember, greater than or equal to 0 is meaning both the normal and the ray direction are pointing in the same direction, or 0, which is it'll never cross the plane. So in either case, if it's 0 or positive, it'll never cross the plane and you won't see the plane. And so we can just exit early. And so go on to the next line and opening curly brace, enter, and then we can just simply return. And what we're going to do here is return a really big number. So in the JavaScript programming language, there's a concept of infinity. And so we can return that huge number of infinity. And infinity, as defined in JavaScript, is guaranteed to be larger than everything else that you could possibly put into your code. And so back in the ray tracing code later, we can just check if this function returned infinity, then we don't need to do anything because the ray didn't intersect the plane. So let's return infinity, and that's a capital I, infinity. And you can click on it here. So it is a number in JavaScript, as you can see here. So click there, and it should highlight it a different color. So that's an actual value in JavaScript. They provide that. So you can do infinity or negative infinity, and so it's guaranteed to be the largest value. And then that was a statement, so semicolon. And so now this code right here provides a nice early out from this function. So if you're pointed exactly parallel with the plane and you'll never cross it, or if you're looking up at the sky and you'll never see the plane anyway, then you might as well not do any further calculations, and you can just return early back to the calling site. So now click here and then hit enter a couple of times. And so now if we get to this point and we've passed this test without returning infinity, and the ray direction dotted with the plane normal is negative, so the plane normal is pointing this way and you're looking down slightly, we can do the actual calculation to calculate the t value for the ray. And so let's go back to the whiteboard and just see what that was. Okay, so we need the plane origin and then subtract the ray origin. So let's get that set up. And here's where we're going to use our variable that we declared earlier, the plane origin, ray origin vector. So let's use that now. Plane origin, ray origin vector. And we're simply going to copy the plane origin. So dot copy opening parenthesis, and then inside those parentheses type plane origin, and that'll highlight this. Now we're using this, which is good. And now semicolon. Now the plane O, ray O, vec holds whatever the plane origin is. And we can safely perform some calculations on this and change it without destroying the plane origin itself that we passed in. So hit enter. I'm going to scroll up just a little bit. Sorry for going back and forth here so many times. So we need plane origin minus ray origin. And so that's plane origin subtract ray origin. So let's perform that operation on the vectors. Plane origin, ray origin vector dot subtract opening parenthesis, and now it says it takes another vector, and so we're going to subtract the ray origin, and that's the only one we haven't used. It's still dark in this list here of our parameters. So ray origin, and now it finally highlights the last one in our list here, and so all these should be highlighted at this point, because now we're using everything that we passed in to this function. And now type semicolon. All right, we're getting closer. So let's go back again to the whiteboard and see what we need to do next. So we just did this subtraction, and see this is in parentheses, so we needed to do that first. And so we have successfully done this subtraction of the plane origin minus the ray origin. And now we're going to need to do a dot product with the plane normal. And once we get that, we can divide it by the ray direction dotted with the plane normal. And recall that we've already done this denominator here. So that was our early out that we tested for back just a moment ago. So we already have this in place. Now we just need to do this vector dotted with the plane normal. And then we can make our final division here and then get the t value. So we're almost there. So hit enter. Now we can use our result variable. Result equals, and then we said we needed to use this vector and dot it with the plane normal. So let's perform that. Plane O, ray O, vec, and then dot, and then the word dot, opening parenthesis, and now it says it takes another vector, so we're going to put plane normal in there. So plane normal. So we're not quite done with this yet, but I just wanted to go over what we're doing so far. So the plane origin, ray origin vector that we just calculated is dotted with the plane normal. And this whole thing right here will return just a simple number, just a scalar number. Now we take that number and divide it by what we had calculated earlier, which is this number, the ray direction dotted with the plane normal. So type ray direction dotted with the plane normal. And now we can hit semicolon. And so basically, we've just accomplished that final calculation back in the whiteboard. Let's take a look real quick. So we did this vector here, dotted with the plane normal, and then we divided by the ray direction dotted with the plane normal. And remember we had already calculated that, so we just used the variable name right there. So it's just a simple division in the end. And so let's go back into the code. So here, this is plane origin, ray origin vector dotted with the plane normal divided by ray direction dotted with the plane normal. And so it's kind of a ratio with the ray origin dotted with the plane normal over the ray direction dotted with the plane normal. So it's kind of like a ratio between those two, and that'll give you a t-value. Now, one last thing to do is to make sure that this t-value is positive and greater than 0, because remember when we discussed the t-value, we need it to be a positive number and never negative. And so remember, if you have a negative t-value, that means the object is behind the ray, and we're not interested in what's behind us or behind the camera. So we only want to focus on what we can see or what the ray can see in front of it. So let's just do one final check here, and then we can exit out of this function. So enter. Now if opening parentheses result is greater than 0, so only if the result is greater than 0 do we want to return the result. So enter and opening curly brace, return result. Now what happens when result is less than 0? So go down, I'm going to scroll down just a little bit and hit enter one more time. So if the JavaScript code interpreter gets here, that means this test did not pass and we should just return an invalid result. So let's do the same thing we did here, return infinity. Return infinity. Semicolon. And so reading this code, we can say if the result is greater than 0, then we can return the result. Now if result is less than 0, it will not execute this and it'll go down to here, which will make it return infinity. If we call this function and we get back infinity for any reason, we know that the ray will never intersect the plane. So it's probably looking up at the sky, or it's exactly parallel with the plane, and it'll never intersect it anyway. And maybe let's just add one more space here between this and the return infinity. That makes it look just a little neater. And with that, we're done with the intersectPlane function. And so, as you can see, it's only a handful of lines of code, but it'll come in really handy for finding that t-value along the ray, and then we can just move the ray out to wherever it intersected the plane, and then do further calculations like a reflection or do a shadow ray towards the light or something like that in the future. All right, are you ready to have some fun? How about we go into our demo file now and visualize a plane in 3D. Once we get that working, we'll add a sky and a ground color and even some fog too. So this is where it's all going to come together. So let's go back into intersectPlane.js. And now that we have all this new infrastructure back in the mathutilities.js file, we can just call those functions in this file here and use all those new features with just a couple of lines of code. So we're only going to add about 10 lines of code to this demo file here, and we'll be able to see a sky with a gradient and a ground plane that fades into the distance as it gets farther from the camera. So let's start by defining a couple of new colors that will represent the sky color and the ground color and the fog color. So let's go right below this color vector here and hit enter. And let's create a color for the sky. Keyword let sky color. equals new vector 3 and opening parenthesis. And now we are going to initialize this with a color that we want for the sky. So through many years of experimentation, I have found that to make a good sky color, it's mostly blue, about half green, and then just a little red. And even though it says X, Y, and Z here, we're going to interpret those as RGB colors. So for the red, let's put a low value, so like 0.2. And for the green color, let's do a little bit above half, so maybe 0.6. And then for the blue color, we want full intensity because the sky is blue, right? So 1.0. And then hit semicolon. And so that'll be a nice bright blue with a little green in it, and then just a little bit of red, just to make it not so overwhelmingly blue and unnaturally blue. But this color choice is definitely a subjective choice, so you may want to experiment with other values for your sky and see if you can make something that you prefer. Next, let's create a ground color. So I'm just going to make this a dark green color, so it'll be like a grassy hill kind of color. So let's go on to the next line and create a ground color vector. Ground color equals new vector 3 opening parenthesis. So let's provide an RGB color for the ground. And usually a green grassy hill is mostly green, maybe like a medium green, and then just a little red and almost no blue. So, and again, this is very subjective, so you may want a different ground color for your ground plane that we're going to visualize in a moment. But I'm just going to put some values in here through trial and error that I've experimented with, and I found this to be a nice green grassy color. So just a little red, so 0.1, and then mostly green, but we do want it to be below half, so 0.4 in this case, and that'll make it like a dark green color. And then just a tad of blue, so we'll do 0.01 type semicolon. And then finally, let's create a fog color. And so typically fog is like a medium gray to light gray. So let's create that on the next line. So let fog color equals new vector 3 opening parenthesis. And now for a gray color, you want all your R, G, and B channels to be the same value. Let's pick something slightly above the middle. So how about 0.7? And that'll be a nice light gray color. 0.7, 0.7, and again 0.7. So now all the red, green, and blue channels are all 0.7. They're all the same. And that'll produce a nice light gray color. Once more, we hit semicolon at the end of the line. So now we've defined all of our colors that we want to use in the scene. And recall that the point of all this new code that we've added is to test for an intersection between a ray and a plane. So for that to happen, we need to define a plane in 3D. And so if we go back real quick to the whiteboard where we talked about defining a plane in 3D, it needs 2 bits of information. So it needs a plane origin, which is this PO right here. And it also needs a normal vector that tells you which way the plane is facing. And so let's go back into the code and add those 2 bits of information so that we can define a ground plane. I'm going to scroll up a little bit and then hit enter a couple of times. And now let's start with the plane origin. So let plane origin. And remember, both the plane origin and the plane normal are vector 3s. So equals new vector 3. Let's make the plane origin right at the center of the world. But I will tell you this, when I was practicing before this video, I accidentally put it at 0, 0, 0 like we had on the whiteboard. And then when I went to run the program, I didn't see a plane, like the plane was missing. And I was like, what happened to my ground plane? Well, I forgot that the ray origin that we have for every pixel is located at 0, 0, 0. So it was at the same point as the plane was. And so that would be like putting your eye like right on the ground plane like this. And therefore, it doesn't pass the test that we had back in the ray plane intersection test, because we tested for if the ray was parallel to the plane, then there's no reason in doing further calculations and we should just exit. So it was exiting early and it wasn't drawing my plane. So what we need to do is, if we don't want to move the eye around, so we're not doing a camera system yet, and we will do that in the future where we can move the eye point around the scene and then rotate and look at different things in the scene. And so I'll show you how to do that in a future episode. But right now, just to keep the math simple, we're going to keep the eye where it is, so 0, 0, 0, which is the center of the world, or the center of our universe here that we're simulating. And then the plane happens to be at the same point, so what we're going to do is just shift the plane down. And so we're going to make its y component of the origin just shift it down negative. And so let's do that here. So we'll do an x of 0, comma, and then how about we move it down like 5 units so we can see it. So -5, comma, 0, and then type semicolon. And so instead of moving the camera around, which will require just a little more math, and we'll do that in the future episode, we're just going to shift the whole Earth down. So we're just going to move the world. This is no big deal. And now all planes need a normal telling you which way they're facing. So the ground plane, as we discussed, so the ground plane is like this. Its normal vector will be like if you stuck a pole right in the ground and it's just pointing straight up. So it'll be like this. And so its components will be x is 0, and then y is 1, and then z is 0. So let's go ahead and put that in our code here. So let plane normal equals new vector 3, opening parenthesis, and let's make this 0 in the x direction, 1 in the y direction, and 0 in the z direction, and then type semicolon at the end. And now I'm going to add one more line that normalizes the plane normal itself. So remember, for the normal direction, it's a direction vector. So we don't care about the length at all. We just are interested in which way the plane is facing. And so we always want the normal to be a unit length of 1. And so let's perform that on the next line. So plane normal dot normalize, using our normalize function that we wrote last time. So opening parenthesis, and it does not take any parameters, as you can see here, so you can just type semicolon at the end. Now that ensures that the plane normal will be a unit vector. And how we've defined it actually is already a unit vector. So the fact that I wrote 0, 1, 0, that's a length of 1 in the y direction, so it's already normalized. But if we change this for any reason, if we put like a 1 here or a 1 over there, it will not be of unit length. And so this line right here ensures that that will happen no matter what values you passed in as the x, y, and z components. And later on, we'll experiment with moving the plane normal around, and we'll kind of tilt the whole Earth a little bit. And so we'll have fun with that. And so this little line here, this plane normal dot normalize, will just take care of that for us. And we can just put random values all over the place and just move around the plane and then not have to worry about it being unit length. All right, so believe it or not, we're almost done. We only need to add about 5 more lines of code and we'll be able to see our plane and the sky and the fog, and everything will recede into the fog as it goes into the distance. So it's all due to the fact that we've added those handy functions back in our mathutils.js file. So let's scroll down here inside the draw function. On the demo from the last episode, we had used this color vector to copy the ray directions and visualize all the ray directions. And if we look back to the demo, it's still doing that right now. So it's visualizing all the ray directions as they fan out from the camera. So let's take out these 2 lines here, the copy and absolute. And if you go back and check the demo, it's going to be all black, and that's to be expected because now we're not setting it to any colors, but we're about to. And then one thing I want to change is making this 0.1 a little bigger. So let's go to -1 in the Z direction. And so as we loop over every pixel, it'll set the ray direction for each pixel to be wherever it is located in the canvas X, and then wherever it is located in the canvas Y, and then it goes -1 in the Z direction, and that's away from the camera, and that's what we want. So all of our rays start at our eye point, and then they go out into the world. And since we have canvas X and canvas Y here, we're sending rays, we're kind of fanning them out. So it starts with canvas X over here, and then it moves like this, and then it goes down canvas Y all the way down to the bottom of the screen. So we'll have a nice fanning effect of all the rays. And currently we're sending out all these rays, but they're not doing anything. So they're just being shot into space, and there's nothing for them to intersect with. So now we're gonna rectify that. Oh, I forgot one thing. Let's go above the draw function and add a variable for t. So let t equals 0. And so t is just going to be a simple scalar number. And now go back to where we were and go right past this normalize here and hit enter a couple of times. And now we get to call our ray intersect plane function. So we're going to set the variable t to whatever the function gives back as the t value. So let's call t equals, and I think we called our function intersect plane. So let's type that, intersect plane. There it is. So click on intersect plane and opening parenthesis because it's a function. And cool, so now it reminds you of what goes in there and what order. So it needs a plane origin, a plane normal, a ray origin, and a ray direction. Oh, you know what? I don't think we have a ray origin defined. So let's go back, because we were just spawning all the rays from 0, 0, 0 implicitly, and so we never defined a ray origin. So we have ray directions, but we don't have ray origin. So let's go and, yeah, that's what I thought. We had defined ray direction, but we didn't do ray origin. So let's just go right above the ray direction line and put let ray origin equals new vector 3, and we'll make all the ray origins 0, 0, 0, and then semicolon at the end. So now all the rays will spawn from 0, 0, 0, which is the center of the world, and we moved our plane down a little bit so we can see it. It's below where our eye is. So now this should all work correctly. So let's go back to the function call. So intersect plane, and it needs the plane origin first. So let's type that. So plane origin, and we had named it that as well, comma. And then what does it need next? Plane normal. So we have that, plane normal. And next it needs the ray origin. So now we've defined that at the top of the program. So ray origin, which is simply 0, 0, 0 every time. And finally the ray direction. And then type semicolon at the end of that. Now the only parameter that will be changing on a pixel by pixel basis as we loop over the pixels is the ray direction. And so see up here, ray direction is constantly being reset to whatever the current canvas X is and the canvas Y is for that particular pixel. So as it moves across the screen, the canvas X will change, and then as it moves down the screen, the canvas Y will change. The Z component will always be going away from the camera. So as we call this intersectPlane function for every single pixel, then it keeps changing this ray direction and giving our intersection routine a new direction to work with. So it'll recalculate that t value for each ray as the ray directions change from pixel to pixel. And now just to visualize if everything's working, let's just say if it hits the plane, we're going to color it white. And if it doesn't, then we're just going to leave it black, like what its default color is. So go on to the next line, and let's test if the t is less than infinity. Because remember, if it's an invalid intersection, so no intersection, it's going to give you back infinity. So to find out whether the intersection is valid, we just need to test if the t value that we got back is less than infinity. And if it is, that means we hit the plane. So if t is less than infinity, and then go on to the next line and open curly brace, enter. And now we can set our color vector. So color vector dot set, and let's just set it to white just to see if everything's working. So that's 1 in every channel. 1 in the red channel, 1 in the green channel, and 1 in the blue channel. And that's full intensity white. And I'm going to scroll down just a little bit here. And now it takes that color vector, whatever we set it to, and it multiplies by 255, and that'll put it into a range that can be displayed on the monitor. And then recall that it floors whatever result that is. So it might be like 207.623 or something. And so it just chops off the 623 and leaves you with a nice integer. And so that's what the Canvas API inside the browser likes working with. It likes working with those whole numbers. It doesn't like the fractional components. So that's why we call this floor function here, just to round it off to the next integer down. All right, so fingers crossed. Let's go back into our web page and see if this worked. All right, we did it. So this is the part where we didn't hit the plane, and then where we did hit the ground plane is colored white. And so it's kind of like if you're like this and you're looking down slightly at the plane. And so this might not look like a lot, but it shows us that everything we've done has been correct. So I'm super excited that this is all working now, because we can build upon this. And now that we can see the plane in 3D, we can add some visual effects to make it look a little more inviting and a little more realistic. So let's go back into the code now, and let's use our sky color and our ground color that we had defined earlier. So let's color the ground plane first. And so how we do that is, instead of set, we're going to call copy. So erase this and then just call the copy function. And we're going to copy whatever we set the ground color to be. So just type ground color. Okay, so let's go back into the demo and see if that's working. We should have a nice dark green color. All right, great. We're getting there. So let's go back into the code. Now we want to provide a clause if the ray does not hit the plane. So what if it's looking slightly up or straight up? We want to color it based on the sky color that we defined. So let's add a else clause here. So go on the next line and then type else keyword. And then likewise opening curly brace. We're going to define what happens if it doesn't hit the plane. So in this case, we want the color vector to be whatever the sky color is. So color vector dot copy, and let's copy the sky color. Semicolon. Okay, so let's go back and check on that. All right, great. Now this looks cool. It's kind of like a retro kind of look. I remember playing games on my old Commodore 64 back in the 80s, and this is what you get if you bought the latest flight simulator. So let's see if we can make this scene a little more interesting and a little more realistic. We can comment out this line here because we're going to do a slightly more sophisticated color calculation. So do a couple of forward slashes to comment that out and then go on to the next line. And now we're going to use our new mix function. And so this is why I went over what the mix was all about and linear interpolation, because we're going to blend the ground color with the background fog color. And so by just calling this mix function, we'll get a really cool effect where if you look at the ground that's right near the camera, it'll be just what the ground color is. But as you look back in the distance, it'll fade off into the fog color. And so it's going to look like there's a mist on the ground. Let's do that here. And so color vector. Now instead of calling copy, we're going to call our mix function that we just implemented. So mix and opening parenthesis because it's a function. Now it reminds you of what it takes. So it's going to take a vector A, a vector B, and a percentage to slide along between those two. And so vector A and vector B can be anything you like, just as long as they're vectors. So we're going to put two colors in here. So we're going to put a color here, and then we're going to provide a T value, which is the ray T itself. So let's put the ground color as vector A. So ground color, comma, and then vector B we'll put as the fog color. So fog color. So these are the two colors that we're wanting to blend. So we have vector A and vector B, ground color and fog color. And we're just going to slide along those two. Now, the amount to slide, it should be based on the distance, right? So we can simply use the ray T value that we got back from the plane intersection and just put that in for the T value here. So comma T. And recall that T was calculated right here in the intersectPlane function. Now, I know ahead of time that this will not work right away. We have to do something to this T value, but let's just see what that does to our demo. So hit semicolon at the end of the line, and then let's go look at that. Well, it changed everything to the fog color. So it's all this nice medium light gray, but that's not what we want. We want the green up front to fade back into the gray as it gets way in the distance. And so what's happening is this T value is really big. remember we said t had to be somewhere between 0 and 1 inclusive? Well, the t that we get back from this intersectPlane function might be like 200 or 3000 or something like that. So it's way beyond 1. And so it's just clamping it to 1 every time. You get a value of 1 to slide over, and you slid over all the way to the fog color. So we're too far to the fog color side. So we need to pull it back into the range between 0 and 1. And so we're going to have to multiply this t value by a really small number. And through some experimentation while I was preparing for this video, I found that 0.008 was a good compromise between the ground color and the fog color distance. So let's try that, times 0.008. And again, that was just through experimenting. So I tried 0.1, then I tried 0.05, and then I kept dialing it down until I got that range to be a good visible range between the two colors. So let's take a look at that now. So it's not going to be perfect yet because we have to blend also with the sky, but we're going to do that in a sec on this line here. So let's go see what that does. All right, that's great. So I know this looks incorrect right now, but it is fading. So it starts right here as full intensity green, or the ground color, and then it fades back and back. And then when you get way back there, it's full fog color, which is light gray. And so now the final thing that we need to do to get this to look really good is we need to blend between the sky and the fog color. Now we can't use the t value anymore because technically up here in the sky, we don't have a t value. It's infinity. We didn't hit the plane. So we can't use any t value, but we can use the ray direction value. So in particular, the y component of that ray direction. So how high are you pointing as you look out into the scene? So right here, the ray direction y value will be around 0 because you're looking straight ahead. And then right here, it'll be maybe like 0.2 or something. And here it'll be 0.5, 0.7, and as you get on up. So it'll keep increasing as you look up and up. And one other thing to consider is that this view doesn't really account for like looking straight up. So we will have to multiply the direction value by another magic number that we decide on. So I'll show you that in a sec. So let's see if we can blend between the fog color and the sky color now. So we have a gray to a blue, and that'll blend everything together. So let's try that. So now take out this line and just comment out this color vector line here. And instead, we're going to use our mix function again. So it's coming in really handy. That's why I added it today. So let's set color vector to be a mix, opening parentheses. And now we want to blend between the fog and the sky. So let's do fog color as our first vector and sky color as our second color vector. And now the t value, or the amount to slide between the two, is going to be the ray direction right here, but only its y component. So we don't care if you're looking to the left or right, or we don't care if you're looking behind you or in front of you. The sky needs to be a certain color all the time, but it does change as you look up. So we only are concerned with the y component of the ray direction. And so let's do ray direction dot y. So ray direction dot y. And I'm just going to leave it like this for now, and we'll go back and tweak it in a sec. But I just want to show you that this will have a cool effect on our final image. Don't forget the semicolon at the end of that line. And let's go take a look at what that does. Oh, wow, look at that. So it's looking, that almost looks like a real sky to me. So it has like the particles scattering that you would get in like a real atmosphere, and then it kind of blends up to a light, nice sky blue as you get up to the top of the image. So just by adding that little mix in there, we've increased the realism like tenfold. So the final thing we can do with this is tweak the amount that it blends up to the top of the image. So if we want it to be more of a full intensity blue at the top, we can kind of just play around with that Y value of the direction. So let's multiply it by a magic number here. And again, this is subjective, so you can try different values on your own and see what you like. So times, and then I'm just going to increase it a little bit, so 1.5. That way it kind of moves up a little faster and you'll get more blue as you go up to the top of the image. So let's go see the effect that had. That's really cool. Wow. So it goes from this hazy, foggy color to a pale blue and to a darker blue, as you would get in real life. When you look out at the sky, it kind of gets more in full intensity blue as you get to the top of the sky. And I really like how this ground fades into the distance. It looks very pleasing to the eye now. So as you follow it back into the scene, it just naturally fades into the foggy color of the horizon. All right, so one last thing I'd like to try is to prove that we're not just cheating and drawing the bottom part of the screen green and the top part of the screen blue, that we actually are firing out a ray through each pixel on the screen and intersecting that ray with a plane in 3D. So how about we rotate the plane just a little bit? So just as we moved the Earth down 5 units, we're just going to tilt the Earth now. So no big deal, right? I don't think the Earth will mind. All right, so go back up to where we defined the plane normal. And now let's tilt it to the right and keep it pointing up. So now it's going to kind of go diagonally up and right. So let's put a 1 here in the X direction. And that's why I have this plane normal.normalize right afterwards, because now this is no longer a unit vector. It's a little too long. So this line ensures that the plane normal is a normalized vector that has a length of exactly 1. So let's go see our tilted Earth now. Whoa, that's kind of cool. So now it looks like we're kind of like tilting sideways, but you'll notice that there is some artifacts now because we didn't fully account for the fog color being tilted as well. So the fog color and the sky color are only based on how high the ray direction is. But I just wanted to prove that we are raycasting against a plane in 3D. And so we can rotate the plane however we like. And so to fix these artifacts right here, the fog that's not blending correctly, that would require another dot product. But I just wanted to show you real quick that this is working. So let's try one more orientation and see if it's working how we expect. How about let's tilt it away from us a little bit. So we'll go -1. So now we've moved the whole Earth to tilt downwards a little bit. And so now we're seeing mostly sky. That actually took care of the artifacts on the left side of the image, but we have this nice gray fog now covering most of the right side of the image. And now let's tilt it back to being flat horizontally. So we'll put a 0 there and let's tilt it towards us. So now the ground will tilt towards the camera and you'll see more of the ground and less of the sky. So let's try that. Yeah, so it's kind of like now we're looking down more and we can barely see the sky at the top. And if we went the other way, -0.5, just tilt it just a little bit away from us. And so now it's kind of like the effect of either looking up or tilting the ground plane down. And so we see more of the horizon color and then more of the sky in the image and less of the ground in the image. So now let's put it back to normal. But that just proves that we're correctly intersecting all the rays with the ground plane out in the scene. And so everything is working perfectly. So I'll change this back to 0. Oh, and by the way, this is why we had to do a negative number here to move the plane down. So if I just kept it 0, 0, 0 and go look at it, you just see sky, there's no plane. So back when I was preparing for this video, I forgot to move the plane down and I was like, where's my ground plane? Where's the earth? But I realized that I needed to move the ground plane slightly down so that the rays will actually intersect with it. Because right now the plane is like right at your eyeball, so you can't really see it. So let's move it back down. Even if we put like -1, you should be able to see the plane. Yeah. But that would be like if your chin was on the ground plane like this. So let's move it down a little bit so that it's more like you're standing on top of the ground. So I just, through experimentation, I just found that -5 was a good amount to move the whole plane down so you could see it. Okay, so I'm really liking how this turned out, and now that we have this in place, we can use this intersectPlane function wherever we like in our future ray tracers. So if we wanted to do like one of those classic scenes where you have like a checkered floor and you have like 2 spheres or something, we'll use this plane function to intersect the plane, and then we'll intersect the spheres, and then we can draw like a checkerboard pattern on the plane itself, and then we'll have a nice stylistic floor for the spheres to rest on. Now I will update the README of our GitHub repositories with this new demo, but in the interest of time moving forward in this video series, I'm not going to show that on camera because I've done that a lot in the past. And so hopefully you have a good idea of how to push these changes up to your GitHub repo. If you're following along and you have your own GitHub repo that you're saving all this to, then you'll be able to do that hopefully on your own. And so each episode I will go behind the scenes after the video is done and upload the changes. But I figured moving forward, we don't really need to see that on camera anymore because I've done it so many times in the past. You can just go back and watch how I do it at the end of all the previous episodes, and I show exactly how to do that. But that'll cut down on the time because these videos have become quite long. But that's just because I really want to explain where all these functions and intersection routines come from. They don't exist in a vacuum and they don't just come out of thin air. There's a reason behind why we use those functions and use those routines to do the operations on the rays in our ray tracers. And so I like to show where that all comes from. But I'm really happy with how the demo turned out today. So we have a cool looking ground plane that fades into the distance, and then we have a sky with a gradient as you go up the image. And so everything is working great, and we can use these routines in our future ray tracers. Well, I hope you had fun with me today in learning how to intersect a ray with a plane. Once again, we covered a lot of topics today, ranging from the dot product to the mix function, to the ray plane intersection function. But hopefully, as you saw, when we actually get down to coding those into our vector library, the code for them isn't that long at all. So oftentimes you'll find that the derivations of all those routines and functions that we talked about today take up much more room than the actual code used to implement them. But I think it's important to go back to first principles and take a look at where those functions come from. So now that we're able to raycast all the pixels rays against a ground plane, we can start adding more objects to our scenes. And that's just what we're going to do in the next video. So in the next episode, we're going to learn how to intersect a ray with a sphere. And once we have all that working with ray versus plane and then ray versus sphere intersections, then we'll have the framework to start building some of those classic scenes that you've seen before, such as two spheres on a checkerboard plane, for instance. So just by having the routine of ray and plane intersection and ray and sphere intersection, we'll be able to create a whole lot of interesting scenes that we can ray trace. So I'm looking forward to doing that next time, and I'll see you then.